Hello, and welcome to Chapter 3. In this chapter, we'll be going over frequency distributions. As a reminder, please check all due dates for assignments that are coming up, and don't procrastinate on doing any of the assignments that are coming up. In Chapter 3, we're going to be going over stem plots, frequency tables, and additional frequency charts. So getting right into it, we're going to be talking about stem and leaf plots. It's a way of looking at the data with graphs and plots. It's one of a more favorable technique looking at single variables. A stem plot is a graphical technique that organizes data into a histogram-like display. And you're going to see what I mean in just a second here. So here's an illustrated example of a stem plot. So we're going to start by saying we're going to select a simple random sample of 10 ages. And we're going to list the data in an order array. Please start doing this now as we get data. Put it in numerical order, like such, going from the lowest value to the highest value. This will help so much more as we move on, especially through the next couple of chapters. So if you don't do it, start doing it now. It's a great way to start organizing data. We're going to divide each data point into a stem value and a leaf value. The way we do this is we're going to take a value of, let's say, 21, and the tens place of the value is 2 for this example. And then you're going to use the ones place as the leaf value of this. And this would be denoted by 2-1. This is how it looks for just 21. If we were to take our data array up here of 05 to 52, it's going to look something more like this. Like this. You're going to plot all the data points and arrange in ranking order. This is why if you have them already ranked order, it's a lot easier to organize them and put them in the stem and leaf plot. A common mistake people make is they don't order the numbers, and as you're trying to do your stem and leaf plot, you'll miss a number because it's not already organized and you forget to leave one out. And this is really going to hurt when you put them in a stem leaf plot and then try to do an interquartile range, or you're going to find the min and max value or the median. These are things that are going to hurt you. So this is what a stem and leaf plot would look like. As you can see, we have 0, 5, 1, 1, and this here's our 2, 1 for 21, and this would be 24, this one would be 27, 28. Now, one way to always look at a stem and leaf plot is to look where this dash is here, and look at the multiplier here. The multiplier is important. If we always read stem and leaf plots to make this dash as a decimal spot and then use the multiplier out, we'll always know what the value is going to be. So for example, if we were to use 3-0 and use this dash as a point, we would say this is 3.0. Use the multiplier of times 10 and you'll see that this is going to be a value of 30, which it is. Here's the plot horizontally, just for demonstration purposes. As you can see, if we flip it horizontally, it starts to look more like a histogram, where these could be the bars for the said histogram. But really what we're doing with stem and leaf plots is we're interpreting them, and one way we can interpret them is with shapes. Things we look for when we're dealing with shapes is the symmetry of it, the modality, which is the number of peaks, the kurtosis, which is the width of the tails, and departures, or the outliers that are in our data. So shape. Shape refers to the pattern when plotted. Mostly we want to look at the silhouette of our data. So here's our data like we just had, but if we were to make a silhouette of it, or a skyline silhouette of it, it would look something like this, right? Around those lines. And as you can see, this would be a skyline silhouette of the data we just put on there. Here we have a histogram with an overlying curve showing a distribution shape. So here we have what you are all going to get very familiar with is a bell-shaped curve, where it goes up, comes down, and it's kind of very symmetrical and even all the way across. We call this a bell-shaped curve. You're going to really get to know this. But as you can see, this is the silhouette of this data. Other types of shapes that we can have, like we said, we just saw an example of a symmetrical bell shape. Remember, symmetrical would be if we took the shape and divided in half, and that has a horrible line. I'll try to do better on the next one. We have even, it's even on both sides. Here we have a symmetrical, but it's not bell-shaped. And that's also a very bad line. I am not a drawer by any stretch of the imagination. Here we have an example of, once again, it's symmetrical, and this is what we call a uniform shape because it's very uniformed and even all the way across and still symmetrical. And then in part D, we have an asymmetrical and bimodal shape where it's not even on both sides, and you can see that there are two peaks to it. Here we have an example of a positive skew and a negative skew. So this is where some people sometimes get confused. Best way I can describe and explain this to help everybody out for positive and negative skew is you're definitely looking at always kind of the tails. And as you can see, this tail is kind of over here, and this is the elongated part on this side. And if we imagine this is our x-axis, and x on the left side would be 0 all the way up to whatever number we want, as it increases, this is more higher numbers, and I'm going to call them more positive numbers, and this is where the positive skew is. Same thing if you were to go to the example F here for a negative skew. If you have your x-axis and 0 all the way to whatever number, and make that infinity, the higher, where the tail is on this end, right, the longer tail part is on more of the negative side, whereas this would be, the positive and negative side of it. This is kind of how I remember it. Might not be the best suggestion. If you have your own method, always encourage you to use your own methods and do it. This is just how I think of it, and it works for me. Modality is the number of peaks. So unimodal is just a una, which is just one peak at the very top, and the bimodal would be two peaks at the very top right there. Kurtosis. So this deals with the steepness, and it's the steepness within the tails. So here's a mesocuric, or a medium one. So the tails here are relatively medium in shape. Here we have platypteric, which is flat tails. These are flat and short tails. Best way to remember this one, I always remember, is like a platypus, and they have very flat and broad tails. So platypteric, or a platypus, has fat tails. And then we have leptocuric, which is a steep one. So these have long and very skinny tails, and this is where tails are. That's how you can judge them. Kurtosis is not easily judged by the eye. A lot of times, you remember, these are the silhouette of the data we're using. You're not going to be able to really see this unless it's actually graphed for you. But once it is graphed, it's a little easier to see. So now we're going to interpret the SEM plots based on location. So now we're going to get into big points here. We're going to talk about the gravitational center, or as we'll talk about it, as the mean, and the middle value, which is the median. And then we already talked about mode a little bit, but mean, median, mode are definitely going to be what we're going to see a lot more in Chapter 4. So the mean is, you can use the eyeball method, so you can visually, it's visually where the plot would balance an arithmetic method, the sum values, and divided by n. So an eyeball method around 20 to 30, it takes practice. So if you were to look at this stem and leaf plot, remember this is kind of a horizontal one, you can see where about the middle is, and it's going to be somewhere, like they said, between 25 and 30, so it's going to be around here if we were to visually look at it. The way you do it, the arithmetic way, is you are going to add up all the values in your data set and divide by the total number there. So if you add up all the total values here, you get a value of 290, and then you're going to divide by 10, which is the total number of data points you have, and you would have your arithmetic method, which would be 29. A little bit more in depth. So now we're going into the location, which is the median. So here we have our ordered array. Remember, it's ordered from our lowest to highest. Very key when we're trying to figure out the median. If the median has the way you figure out where the median is you take the depth of n plus 1 divided by 2 on the ordered array. Remember, we talked about n being the total number in the data set. So our n here is going to equal 10. When n is even, the average of the points adjacent to the depth. So what this is telling you is how many spaces in you have to go to find the median value. So here's the illustrated data, n equals 10. The median depth is 10 plus 1 divided by 2, which equals 5.5. The median falls between 27 and 28. So let me show you how this works. So the median depth is 5.5. So you would count in 5.5 numbers in. So here's your 1, 2, 3, 4, 5.5 would be right here. Since there's actually not a true number right here, the way you'd find the median is you add these two together and divide by 2. That's when n is even. If n is odd, when you do define the depth of the ordered array, it will land on a specific number, and that number is your median. Interpreting the stem plot spread. So other terms to know: range and interquartile range. Interquartile range is always IQR. And standard deviation and variance, which we'll go into more detail in chapter 4. So for spread, the range is equal to the maximum to the minimum. It's easiest but always the best way to describe the spread. There are better methods of describing it, and we'll talk about more of those in the next chapter. So for the illustrated data, the range is from 5 to 52. Like we said, if we were to go back to our ordered array, you see the minimum value is 5 and the maximum value is 52. We would say the range is from 5 to 52, just like that. Here we have a second example now for our stem plot, and here's our data. So you can see the data is already organized for us from the lowest to highest. The stem is going to be the ones value in the ones place, and the leaf is going to be the number that follows. For us, it's going to be after the decimal point. The leaves are going to be the tens place. As you can see, there's an extra value when we're coming to decimals. There's 1, 2 decimals out. So what we're going to do is you're going to tourniquet the extra digit. Basically, you're going to cut it off. It's not going to be part of this example. So the way you do it is here you have your tens column, and here you have your ones column, and then here's our dash, or as we're going to express it as decimal. Our multiplier is times 1. So if we were to take an example of 2.0 or 2.3, and when we do that times the multiplier, it still is 2.0 or 2.3. And that's all you need to know for the stem and leaf plot. Other things to look at for the stem and leaf plot, the center will be between 3.4 and 3.8, which is what it's underlined here, and the spread is going to be from 1.4 to 4.4. If you wanted to do the silhouette drawing, you would just kind of go like that, and you can see it's a mound shape, fairly symmetrical, and no apparent outliers. Here's another example, and actually I'm going to save this for the next video. I'm going to pause here because I don't think I'll be able to finish the next part in this next clip for the purposes of YouTube length. So I will pause here and then put up a second video going over the third illustrated example. See you in the next video.